This is a reminder that you should feel free to take as much time as you need to write all of the notes down and think about them. Pause the video at your own pace.
Welcome, you cool cats, to section 4.6, day 1, division of polynomials. First of all, what I want to do is I want to talk to you about, before we divide polynomials, let's just remember what it's like to divide integers and whole numbers. So, like we have here, if we want to take 140 and divide it by 5, then we know that we have 5 goes into 14 twice, minus 10 is 4, bring down the 0, we got 8 times 5 is 40, and then 0 with no remainder. So 140 divided by 5 is 28, and the answer is up here. If you do the same thing with 142, you'll get the same results, except that there's going to be a remainder of 2 here. And that's one way to express a remainder, but another way would be to say that it's 28 and 2/5, because we have the 2 here and the 5 here. That's all well and good, and I know, of course, you can all do that because you're in high school now. But I wanted to remind you of that because we're going to do a very similar thing with polynomials next. Now, why is it important? It's important because we often want to take numbers like 140 and put it into factored form. Factored form like this would be reducing it all to the different factors, 2 times 2 times 5 times 7. And once it's in factored form, you can do lots of things with it, like you can find the primes, the least common multiple, the greatest common factor. And in fact, all of internet security, like anytime you've ever purchased anything, anytime you've ever made any transaction, anything involving encryption whatsoever, anytime you sent an email with Google, it's been encrypted. And the ability to encrypt things rests upon the difficulty in factoring really large numbers. Put it another way, if you could factor any number you wanted, regardless of how big it was, like astronomically large number, if you could actually factor that, then you could essentially crack any encryption scheme that Google or Bank of America could ever put forward. The NSA, as far as we know, the NSA can't do this. So putting things in factored form is actually incredibly difficult, incredibly useful, and because it's so difficult to do, then we have internet security. One thing that I do want to note is that the types of coefficients that we're going to be using is going to fluctuate throughout the course of this section and throughout. So you have to kind of read the instructions. We will be allowing for complex coefficients here. Sometimes if the instructions say that complex are allowed, then this is what it could look like. If it's only real coefficients, and this is what it could look like. These are all real numbers here as coefficients. Sometimes they're just going to be rational coefficients, which means we're fractions only, and then sometimes they're just integer coefficients. So you kind of have to remember that this is the kind of thing that's going to be in flux, and you have to always pay attention to it. Isn't that great? Awesome. So let's put in factored form to find the zeros. Let's change this. The goal is to change this into this, because if we have the factors, then we can find the zeros and the intercepts and the solutions. So factoring a polynomial is incredibly important because it'll tell us where the x-intercepts are, where the solutions to the equations are. And if we can do that, then things are going to be a lot easier. So how do we put it in factored form? Oh yeah, so as I said, once it's factored, then you can say that the zeros are -3 and -1 and +2. So the whole trick is going from here to here, and so we need some new skills. We need to develop some new techniques for doing that. Let me show you what division of polynomials looks like, step by step. First step is to ask yourself, how many times does x go into x cubed? It goes in x squared times. In other words, x times what gives you x squared? It's x cubed. But there's also this 1 over here, so when we multiply x squared times x, we do get x cubed, but x squared times 1 is going to give us 1x squared. Now, in normal integer division, like I showed you with 140 and 142 above, at this point what we would do is subtract. And we're going to do the same thing here. I find that it's a little easier to think about it in terms of adding the opposite. So we're going to subtract these two polynomials by changing the sign and then adding them. 2x squared, and I even circle that to note that when I look back in my work, I'm able to see that I changed the sign and then I added. So x cubed plus negative x cubed is 0. They cancel. It's designed to cancel that way. They'll always cancel if you do it right. And then 2x squared plus negative 1x squared is 1x squared. Now you might say, Bergman, isn't it just easier to say 2 minus 1? Well, yeah, in this case it is, but this number right here is not always going to be positive, and this number is not always going to be positive. So I find it easier just to make sure you change the signs and add. Minus 5x. So you ask yourself, what, let's see, x times what will give you 1x squared? That's going to be 1x. 1x times x is, you can just write x if you want. X times x is x squared. And then x times 1 is 1x. And now we're going to change the signs. Change all the signs so that we can, in effect, subtract. And so now here we're going to add these together. 1x squared plus negative 1x squared cancels. Negative 5x plus negative 1x is negative 6x. And you bring down the minus 6. Then you say x times what gives you negative 6x? That's negative 6. 6 times x is negative 6 times x is negative 6x. Negative 6 times 1 is negative 6. Change the signs, and we get positive 6x, positive 6. And when you add, they cancel. And so therefore, we're done. We can say that this entire polynomial divided by this smaller polynomial is this polynomial right here. Now, why is that so significant? It's because you can write, it's significant because it's how we started to factor this in the first place. If you're looking to factor h of x is equal to x cubed plus 2x squared minus 5x minus 6. Well, we found that when we divided out x plus 1, we got x squared plus x minus 6. So all of this became all of this, which is one step closer to being factored, which is our goal. We want to continue to factor. You could use a factor x to factor this, and you get x plus 3 and x minus 2. I got that by doing factor x on this right here and turning it into x plus 3, x minus 2. So therefore, this polynomial division is one more way to help you factor polynomials. Let's take that same polynomial again. It's the same polynomial, and divide it by a factor that is not here. So we can see x plus 3 is present in the factored form. Let's see what happens if we were to divide it by something that doesn't evenly factor it in. So the analogy is we just did 140 divided by 5. We got something with no remainder, 28. Now let's see what happens when you take something that will produce a remainder. So walking through step by step, we have to ask ourselves, x goes into x cubed how many times? X squared times, because x times x squared is x cubed. X squared times negative 3 is minus 3x squared. You change the signs. This one becomes negative, this one becomes positive. And you add 2x squared plus 3x squared is 5x squared. Bring down the minus 5x. You ask yourself, x times what gives you 5x squared? That's 5x. So 5x times x is 5x squared. 5x times minus 3 is minus 15x. And then you change the signs. Cancel, change the signs here. Minus 5x plus 15x is positive 10x. Ask yourself, x times what gives you 10x? That's 10. 10 times x is 10x. 10 times minus 3 is minus 30. And then you change the signs. Minus 10x and plus 30. So minus 6 plus 30 is 24. And that's actually going to be a remainder, because we go to remainder of 24. This was just the number, and we can't go any further. If you tried to go further, you could say the remainder, you could say this is x squared plus 5x plus 10 plus the remainder 24 over what we were dividing, x minus 3. Very similar to what we were saying here. When we were dividing by 5, the remainder could be expressed as 2/5, because you had a remainder of 2. Let's try it again. We've got x cubed and x here. So x times what gives you x cubed? That's x squared. X squared times x is x cubed. X squared times minus 2 is minus 2x squared. Change the signs. We got minus and plus, and so 2x squared plus 2x squared is 4x squared. Then what goes into x times what gives you 4x squared? That's 4x. 4x times x is 4x squared. 4x times minus 2 is minus 8x. 5x plus 8x gives you 3x. X times what gives you 3x? That's 3. So 3 times x is 3x. 3 times minus 2 is minus 6. Change the signs. Minus 6. We bring down the minus 6, and then this minus 6 plus 6 is 0. There's no remainder. And that's how. It's just one more way that we could find that one of the factors here of this function is x minus 2. You could further factor this, x squared plus 4x plus 3, into x plus 3 and x plus 1 using the factor x. So just some terminology here. I've color-coded it. If you've got a polynomial and you divide it by another polynomial, you could get a remainder, or you could get just this quotient right here. Here are the words. The dividend here is equal to the divisor times the quotient plus the remainder. Synthetic division. Now, one thing you might have noticed is that there's a lot of handwriting that's going on. Synthetic division is this awesome way of eliminating the handwriting. And so you can see, I mean, this is what the work looks like. There's no x's anywhere. It's that we're going to do the same exact thing. We're going to do the same. It's the same goal to produce the factors, but we're with a minimal amount of handwriting. There's not even any subtraction. It's all using addition and multiplication. So that makes things a lot easier also. I want you to notice some things here. If you're dividing this by this, it translates to this. So 4 minus 3, there's an invisible 1 here and a 7. You would write 4, negative 3, 1, 7. And then if you're dividing it by x minus 2, then you put positive 2 here. Notice that we're using the 0 and not the factor. So the factor, when you write it here, the factor is x minus 2. You might think that minus 2 here, but actually use the 0. It's the opposite, positive 2. Now the down arrows are going to represent addition, and the diagonals are going to be multiplying by the 0. So when you set it all up, this is what it looks like. 4 gets brought down. You multiply 4 times 2 to get 8. You add these 2 to get 5. You multiply these 2 by 2. You add. You multiply by 2. You add. So, and the remainder is 29. The answer here could be reinterpreted as 4x squared plus 5x plus 11 with a remainder of 29. Let me show you what that looks like. Let's say you had to do this polynomial division. Well, it's a lot easier to set up this synthetic division. And so I'll do this one out. You've got x plus 1 here, so the 0 would be -1, and that's what we're going to use here. You can draw the line. You can draw this line right here. The coefficients come from 1, 2, -5, and -6. We just write the coefficients out here. And so the steps say add this. Well, just bring down the 1. There's nothing to add. And then multiplying 1 times the 0, -1, is -1. Then you add. You multiply by the 0. Then you add. This is actually going to be +5. Sorry. You add to get -6. And then you multiply by -1 to get +6. And then you add to get a remainder of 0. You can reinterpret the answer as -6 is the constant term, 1x is the linear term, and 1x squared is the quadratic term. So that's the answer, and there's a remainder of 0. If you wanted to divide this polynomial by this polynomial, it's right here. Let's do some more. Here it's all written out. So if you just translating first the polynomial, you can see here, if you want to take this entire polynomial and divide it by x minus 3, you translate the divisor by, the factor is -3, has a -3 here, so the opposite of that would be +3, that's the 0. The invisible coefficient is 1, 2, -5, -6. And so, by the way, if there were no term, let's say it was just x cubed and then -6, without these terms here, you would have to write a 1 and then a 0 and then a 0 and then a -6 to hold the place values. That's what I've written right here. Insert a 0 if there's no terms. So if it was just 3x squared minus 27, you'd have to translate that as 3 with a 0. 0 is a linear term. It's not present. You don't see it. And then minus 27. Okay, so we've got it all translated here. And then the first thing you do is bring down the 1. You multiply it by the 0. Add. Multiply by the 0. Add. Multiply by the 0. Add. And to retranslate these numbers back into the polynomial, we'd have 1x squared, 5x, and 10, with a remainder of 24. People often draw this little line right here to separate out the answer from the remainder. Now, you could write the answer like this, or you could also technically write the answer like this: x squared plus 5x plus 10 plus the remainder 24 over x minus 3, which is what the divisor was. Let's do one more. If you want to translate this division into synthetic division, we've got the coefficients here of 1, 2, -5, -6. The 0 is 2 here. Then we're going to add, or just bring down the 1, multiply by the 0 to get 2, add, multiply by the 0, add, multiply by the 0, add, and you get 0 here as a remainder. I would like you right now to translate this polynomial, just like President Jimmy Carter learned how to do when he was taking Algebra 2. Jimmy Carter learned how to translate polynomial division, synthetic division into polynomials, and I'd like you to do that right now also. So, just like we translated this into this, I would like you to translate this into something on your notes, and I would like you to then start assignment 4F1. Copy the problem list and do the first problem. I will see you in class.